Hello fellow math, I am Dr. Vilva and meet my friend Brinda.
Hi, you just found me in UK, that is unknown to known channel. Here, numbers stop being scary and start to say story. Let us involve, learn and win.
In this video, we are going to study irrational numbers. We will revisit a few concepts you have studied previously, focusing on specific theorems and problems to help you practice. Let us start with a reminder. An irrational number is any number that cannot be written in the form p by q. Here, p and q are integers and q should be non-zero. First, we are going to prove that the square root of a prime number is irrational. To do this, we will use the fundamental theorem of arithmetic. Before we begin, we need to prove a theorem which states if p divides a square, then p divides a. We will examine the proof for cases where a is either a prime or a composite number. If a is prime, the proof is trivial because a naturally divides a and a is a prime number. However, if a is composite, we can use the fundamental theorem of arithmetic to express a as a product of primes p1, p2, etc., pn, where these primes are not necessarily unique. We can write a square as a times a, and a is a product of prime numbers p1, p2, etc., pn. Therefore, a square becomes p1 times p2 times etc. pn. This complete primes will be multiplied with itself. This simplifies to a square equal to p1 square times p2 square times etc. pn square. Our theorem states that p divides a square. That is the data, which means p must be one of the prime factors of a square. According to the fundamental theorem of arithmetic, prime factorization is unique. Therefore, the only prime factors of a square are p1, p2, etc., pn. From this, we can conclude that p must be one of the primes in the set p1, p2, etc., pn. Since a is p1 times p2 times etc. pn, it follows that p divides a. Please keep in mind that rational numbers are written in the form a by b, where a and b are integers. In some cases, a and b might both be prime, like 2 by 3. 2 is a prime number, 3 is also a prime number. In other cases, they are co-prime, like 2 by 21. 21 is not a prime number, but 2 and 21 are co-prime, meaning they share no common factors other than 1. In both these examples, no further simplification is required. However, if a and b have a common factor, for example 4 by 6, we must simplify by dividing both by their common factor 2. It reduces to 2 by 3. For our proofs, we will always assume the rational number is in its simplest co-prime form. Conversely, if a number is irrational, it cannot be written in the form p by q at all.
I know that square root of 2 is irrational, a decimal that goes on forever without a pattern. But how do we actually prove it?
Let us prove that the square root of 2 is an irrational number. To do this, we will use a powerful logical tool called the method of contradiction. This means we will start by assuming the opposite is true and then show why that assumption leads to an impossible result. First, let us assume that square root of 2 is a rational number. If that is true, we can write it in the form r by s, where s is not equal to 0. Now, r and s might have common factors or they might already be co-prime as we discussed earlier. If they aren't co-prime, we can simply cancel out the common factors until we reduce the fraction to the simplest form a by b. At this stage, a and b are co-prime, meaning they share no common factors other than 1. So, we have square root 2 is equal to a by b. If we cross multiply b with square root 2, we get b times square root 2 is equal to a. To get rid of the square root, let us square both sides of the equation. This gives us 2b square equal to a square. Now, look closely at 2b square equal to a square. Since 2 is a factor of the left side, a square must be an even number. Using the theorem that if a prime divides a square, it also divides the base. Using our previous proof, we know that if 2 divides a square, 2 must divide a. Because 2 divides a, we can write a as 2 times c, where c is some integer. Now, let us substitute a is equal to 2c back into our equation. 2b square becomes 2c whole square. In place of a, I have substituted 2c. Therefore, 2b square becomes 4c square. If we simplify this by dividing both sides by 2, we get b square equal to 2c square. Just like before, this shows that b square is even, which means 2 must also divide b. Here is the problem. We just showed that 2 divides a and now 2 divides b. This means a and b have a common factor 2. This contradicts our very first step where we reduce the fractions to its simplest form and stated that a and b are co-prime. Because we hit this contradiction, our original assumption must be wrong. Therefore, square root 2 cannot be rational. It is irrational. You can use this exact same method to prove square root 3, square root 5 or square root 7 are irrational. The logic remains the same for all square root of a prime number.
What happens when I add or subtract rational number with a irrational number? Otherwise, if I multiply or divide rational numbers with a irrational number.
Good question, Vrinda. The sum or difference of a rational and an irrational number is irrational number. In the same way, the product and quotient of a non-zero rational and irrational number is irrational.
Can you give some example to make this clear?
Sure, Vrinda. Let us explore what happens when we subtract an integer from an irrational number. We will find that the result is always irrational. Let us consider an example. 5 is an integer and root 3 is an irrational number. We want to prove that 5 minus root 3 is irrational. To do this, let us use a proof of contradiction. Suppose 5 minus root 3 is actually rational. If that is true, we can write it in the form a by b, where a and b are co-prime integers and of course b is not equal to 0. Mathematically, we can set up the equation 5 minus root 3 equal to a by b. If we rearrange the terms, we get 5 minus a by b equal to root 3. After finding a common denominator, the equation becomes 5b minus a whole divided by b equal to root 3. Since a and b are integers, the left side of the equation is a rational number. However, this forces root 3 to be rational, which we know is a contradiction. Root 3 is an irrational number. Therefore, our initial assumption was wrong. 5 minus root 3 must be irrational.
Can you give example for the second case, Vilva?
Of course, Vrinda. Now, let us look at what happens when we multiply an integer by an irrational number. For example, if we take the integer 7 and the irrational number root 5, the product 7 times root 5 is supposed to be irrational. To prove this, as usual, we will use a proof by contradiction. First, let us assume the opposite. Suppose 7 times square root 5 is a rational number. If that is true, we could write it in the form a by b, where a and b are co-primes. Of course, b should not be equal to 0. By rearranging the terms, we get square root of 5 is equal to a by 7b. Since a and b are integers, a by 7b must also be a rational number. But this leads us to a problem. Our equation now claims that root 5 is rational. This directly contradicts the fact that root 5 is irrational. Because we have reached a contradiction, our original assumption must be wrong. Therefore, the product of an integer and an irrational number must be irrational. Successfully, we have completed the first chapter. Important things to remember. Euclid's division algorithm. Any positive integers a and b is divided. If a is divided by b, then we can write a as b times q plus r. R is the remainder. R can be 0 to some integers which is less than b. Next is fundamental theorem of arithmetic. Every composite number can be written as a product of primes. We have seen some properties. HCF of A, B times LCM of A, B is equal to product of A and B. We have studied few theorems. If P is a prime number and if P divides A square, then P divides A. Root P is irrational, where P is any prime number. The sum or difference of a rational and an irrational number is irrational. The product and quotient of a non-zero rational and irrational number is irrational. LCM of P, Q, R is equal to P times Q times R times HCF of P, Q, R all divided by HCF of PQ times HCF of QR times HCF of PR. I have given some problems for practice here. You can discuss the solutions in the comment box. In the next video, we will discuss previous year question papers, the problems which covers on first unit. Thank you.